If you look toward the western horizon shortly after sunset, you can often spot a brilliant, steady point of light piercing the twilight. For millennia, human beings have watched this serene beacon and called it the evening star. That light is Venus. Because its orbit sits closer to the sun, it never strays far from our star's glare. It reaches its peak visibility at a point called greatest elongation, stretching to an apparent distance of roughly 46 degrees before swinging back. This data table outlines physical parameters for both worlds. The top rows show a nearly 1-to-1 ratio in radius and mass, but the twin illusion evaporates further down. Venus experiences a 464-degree surface temperature and a crushing atmospheric pressure 92 times heavier than Earth's. The starting materials were identical, but their destinations were different. Earth buried its carbon deep inside rocks and oceans to foster life. Venus released its carbon into the sky, creating a toxic, heat-trapping illusion of serenity. Between 48 and 70 kilometers high, the atmosphere manifests as an unbroken layer of sulfuric acid clouds, completely obscuring the crust from visible light telescopes. Yet within these upper, temperate cloud decks, researchers recently detected traces of a highly reactive gas, phosphine. In the oxygen-poor depths of Earth, phosphine is produced by anaerobic microbes. On Venus, the oxidizing environment should rapidly destroy it. Exhaustive modeling has ruled out volcanic outgassing, lightning strikes, and meteorites as sufficient mechanisms to maintain the concentrations observed. Identifying this mysterious source requires long-term monitoring. Programs like the JCMT Venus project use radio telescopes to measure how phosphine shifts in relation to other chemicals, like sulfur dioxide, over years of atmospheric circulation. Decoding this chemical fingerprint is about more than finding a single gas. It allows scientists to build more accurate models of how the atmosphere evolved. By understanding how such a reactive chemical persists today, researchers can work backward to determine when the runaway greenhouse effect permanently altered the planet's chemistry. The sulfuric acid layer creates a massive planetary blind spot. We cannot rely on traditional optical cameras to document the geological history scattered across the Venusian crust. To bypass this barrier, NASA is developing the VERITAS orbiter. It is a highly advanced spacecraft designed to finally strip away the dense clouds and read the rocky surface directly from orbit. VERITAS will utilize interferometric synthetic aperture radar, or InSAR. It beams precise radio frequencies through the atmosphere. By measuring the timing and phase of the returning echoes, the orbiter constructs a high-resolution, three-dimensional topographic grid of the surface below. Operating alongside the radar, an onboard infrared spectrometer will scan the night side of the planet for thermal emissions. This allows researchers to detect active surface deformation and flag anomalously hot, fresh lava flows erupting in real time. VERITAS is not simply taking photographs, it is translating an invisible, hostile world into readable geological data. To test that translation, the engineering team traveled to the harsh, fractured lava fields of Iceland in August of 2023. Scientists used this specific extreme terrain as a terrestrial analog for the Venusian surface. Researchers mounted radar instruments onto heavy-lift drones to simulate the orbiter's path. By comparing these radar returns against the physical rock formations on the ground, they can ensure the spacecraft will accurately read geological anomalies from orbit. Simulating the extremes of Venus here on Earth is the only way to guarantee the mission's forensic accuracy. Once we reach the crust, the most obvious discrepancy between the two planets is structural. Venus lacks Earth's system of moving, interlocking tectonic plates. Because the planet rotates extremely slowly, it fails to generate the global magnetic dynamo required to drive deep mantle convection. Without plate tectonics to vent the interior, the planet has no mechanism to release internal heat. This is a radar-generated view of Mont Mons, an 8-kilometer-high volcano. With no tectonic boundaries to release pressure, trapped heat forces its way through the crust via massive mantle plumes, creating vast fractured plains dominated by magma. Geologists refer to this as a stagnant lid regime. The entire outer lithosphere remains a single, unbroken shell that buckles and erupts in localized hotspots rather than drifting. This stagnant reality is the primary engine driving the evolutionary divergence between Earth and its twin. Before Earth developed its modern continents, it likely functioned in a similar way, hotter and driven by volcanic plumes. While Earth transitioned to plate tectonics, Venus became stuck in an earlier stage of geological evolution. This makes Venus a natural laboratory for studying our own planet's deep past. It demonstrates the catastrophic endpoint of an unchecked greenhouse effect on a world that never found a way to recycle its carbon. And when we look back up at the night sky, the bright evening star is no longer a serene illusion. It is a crucial planetary warning sign waiting to be decoded.